In this video, we're going to discuss objects in Python. We've referred to objects many times in previous notebooks, and here we're going to attempt to define this more clearly. Objects are Python's abstraction for data. In fact, all data and the relationships between them are represented by objects in Python. Objects have three basic parts: identity, type, and value. The first part, identity, is unique to an object, and it never changes once it's created. The ID function can be used to get an integer representation of the identity of an object. So for example, if we were to bind the name x to an integer, we can then output the ID of that integer. Now note that the ID function is returning the ID of the object representing the integer 529485 and not the name x. So the variable x is not like a box, let's say, that holds the integer 529485. Instead, it holds the identity of the object to which it has been bound. And so this sort of points to or refers to the object via its ID. So to see this, let's write y equals x, and then we're going to call ID again, but this time with the name y. And when we run this, you see that we get the same ID output, even though we're using the name y instead of the name x. The names x and y are actually independent of one another. And we could, of course, bind y to some other object, and it would not affect the contents of x. So when we pass these names to the ID function, we're getting the identity of the object to which those names are bound. Now, if I were to repeat the first example using the same integer and a new name, so if I wrote z equals to 529485, which is the same number that we previously bound x to, and then output the ID of z, you see that a new object has been created to represent this number, and it does not match the ID that was output in the previous two blocks. And this is because, in general, when an object is created, it is given a unique ID. And so even though we're hard-coding the same integer as before, this is a new object in Python. And so we see a new ID given here. In a previous notebook, we briefly introduced the is and is not operators. These operators compare the identity of objects. And this is not the same as comparing the value of objects. So to show you this, let's write x is z. This returns false because the name x is bound to a different object than the name z. We know this because in the previous examples, we output both their identities and we saw that they were different. So the is operator is effectively checking if the objects bound to x and z have the same identity, which they do not, even though in this case, they have the same value. So if we were to write x equals z, we see that this returns true. The equality operator is checking if the two objects have the same value, regardless of whether they are the same object or not. This is why it's important to not confuse the is and equality operators. They may appear to be interchangeable, but as we just saw, they are actually quite different. Now, the second part of every object is type. The type of an object determines the operations that it supports, as well as the set of possible values that it may take. An integer object, for example, may take any integer value, but it may not take a string or character values. So the type integer in that case is effectively restricting what values can be stored or represented by integer objects. Likewise, operators like plus or minus have certain meanings with integers like addition or subtraction, but we cannot use the plus operator to append more integers like we would with strings. So the set of operations is also limited or defined by the type. The type function can be used to return the type of an object. And we actually used this previously in the data structures chapter to demonstrate proper and improper instantiations of objects containing single elements like sets or tuples. So for example, the type of x here is int or integer. Also, type cannot be changed for an object once it has been created, just like the object's identity. Now the third part of an object is its value. Values can actually change for mutable objects, and obviously not for immutable objects. The mutability of an object is determined by its type. For example, strings, numbers, and tuples are all immutable, while lists and dictionaries are mutable. Now, if you recall from the notebook on tuples, we demonstrated that even though a tuple was immutable, we were still able to modify its elements if they themselves were mutable. So now with the concepts of identity and value here, we're going to take another look at how that actually works. Okay, so let's define a tuple T, and we're going to give it three elements. The first is going to be a list containing 1, 2, 3. The second will be a string containing the character A, and the last will just be an integer 5. The first entry here is mutable, and the other entries are immutable types. We already know that we can't modify a tuple by adding, removing, or even replacing any of the elements, but we can modify the contents of its first element here, the list. So we saw in the previous notebook on tuples that the following works, where I'm replacing the second element of the list with the integer 5. So once again, why does it appear that we were just allowed to modify our immutable tuple? Well, the answer to this comes down to what is the actual value being stored within a tuple? A tuple is a container, meaning that it contains or stores other objects. To do so, however, it actually stores references to those objects, which really means it's storing the identities of those objects. Just like our name x stored the identity of the integer in the first example, this tuple is storing the identity of a list, a string, and an integer. So to see this, let's recreate our tuple. And in the second line that I've pasted here, you see that I'm printing out the ID of every element in the tuple. So I have here the ID of the first element, the ID of the second element, and of course the ID of the third element. Now, before we run this block, let's also add the line where we modify the list, and then we'll print out the identities again. If we look at the output here and we compare the identities for each element in these two lines, we can see that there's no differences between them. So even though there was a change made to the list object itself still has the same ID, and the tuple still refers or stores that ID. And so the apparent change to the tuple is allowed because the tuple really isn't changing. Only the object that it points to is changing. A misunderstanding of the value that is stored by some objects can lead to unexpected errors or at least confusion about various types. The next notebook on assignments and copies will also touch on this concept, but will include a discussion of shallow and deep copies and how the storage of identity plays a role in both of those operations. Now, to wrap up this notebook, in many languages, there's an explicit creation and destruction of objects that is prescribed by the programmer. While the programmer does explicitly create an object by defining it in Python, the programmer is not actually responsible for cleaning up or explicitly destroying all objects. Python actually keeps track of whether or not each object is reachable, meaning can the object be referenced or used at any point in the code? And when an object is no longer reachable, then Python is actually free to remove it. And this sort of automated removal is commonly referred to as garbage collection.